Okay, in today's class, what I'm going to do is I'm going to talk about some very simple problems in dynamics. Robot dynamics problems are not simple uh, and not they are not easy. But what I want to do is I want to talk about a very simple dynamics problem, and I would like to obtain the equations of motion using multiple techniques. And I want to introduce you to a very, very powerful technique, which is called as conservative laws. Okay, so, all right. So, so today we are going to talk about robot dynamics. And if you have taken physics 321, I'm going to discuss the content of physics 321 from engineer's point of view. So let me start with Newton's law. Newton's law says summation of forces is equal to mass times acceleration. Force is a vector, acceleration is a vector, mass is a scalar. So this is a vector equation. What do we mean by vector equation? Which means if you have force expressed in 3 dimensions, that is related to the mass multiplied by the acceleration in that respective direction. So this expression can be simply written as summation of forces in x direction is equal to mass. Mass is same in each direction multiplied by acceleration in x direction. This equation can be represented as summation of forces in y direction is equal to mass times acceleration in y direction. Summation of forces in z direction is equal to mass multiplied by acceleration in the z direction. Now, one important thing to observe is since this is a vector equation, definition of coordinate system is super duper important. What do I mean by that? And even though this is sort of, we take it for granted that you know it, but I just want for my own satisfaction, I just want to show you what it means. We are always going to use a right-hand coordinate system. You are going to have an x-axis, you are going to have a y-axis, and you are going to have a z-axis. Now, x-axis, you will have a unit vector I. Unit vector has magnitude 1 and it is indicative of direction. Y-axis will have unit vector j and the z direction will have unit vector k. Now, force is a vector. What that means is if the direction of the force is in the same direction as the axis, that force is positive. As a matter of fact, acceleration is also a vector. If the direction of acceleration is aligned with the direction of the coordinate system, that vector or that acceleration is positive. Same thing happens with velocity. Same thing happens with jerk. Any vector quantity where the direction is aligned with the coordinate system, that vector quantity is going to be positive. And this is simple, but very, very important when we actually decide the forces and the moments. Now, let me take a very simple example of a spring mass system. Now, so this is ground or fixed support. This is the spring, and you have the mass which is attached to the spring. So this spring has stiffness K. This is mass M. So K is called as the stiffness. So stiffness means whether the spring is hard or soft. And that is given by this classic expression, force divided by deflection. Force is given in Newton, deflection is given in meter. So spring stiffness is given in Newton per meter. And this equation, this relationship sometimes is expressed on force versus displacement diagram. And for a linear spring, this is a straight line. And this ratio is called as K, or stiffness. So this is the slope. Now mass is expressed, M stands for mass. That is given in kilograms. Now what I want you to understand is this mass initially is at rest. This mass is initially at rest. This rest position is called as the static equilibrium position. Static equilibrium position. Now what I'm going to do is I'm going to pull this mass on one side and let it go. So I will pull this mass on one side and let it go. What would happen? You agree with me that this mass would start oscillating front and back. So this mass will start oscillating front and back. And this motion is going to be harmonic, sinusoidal, and repeating. Imagine the spring mass system is placed inside the vacuum. If this spring mass system is placed inside the vacuum, which means there is no dissipation element, there is no air resistance, these oscillations will continue for the infinite period of time. Which means what will happen is I pull the mass, let it go, and it will continue to oscillate back and forth, back and forth, back and forth, because essentially what is happening is you have this interaction between the kinetic energy and potential energy, and this continuous exchange of energy sets this mass in motion. Let me explain the physical phenomenon, because that is the stepping stone for the conservative laws, the laws that govern us, the laws that govern the universe. So here is what is happening. Initially, you have the static equilibrium position. I pull the mass, and this mass goes on to this position A. This mass, I'm going to call this mass going on to position A. At this position A, do you agree with me that this spring is completely stretched? The spring is stretched, which means now the spring is storing energy. As soon as I release the mass, this spring is going to pull this mass back. And what would happen is this mass would continue point B. So now the mass is going from point A, it's going to point B, but at point B, the spring is neither stretched nor compressed. Okay, at point B, the spring is neither stretched nor compressed. But because of the inertia, the mass has the maximum velocity at point B. Because of the inertia, so at one point, the mass is stationary, kinetic energy is 0, but the potential energy is maximum. You let that mass go, and then kinetic energy increases, potential energy goes to 0 at point B. So at point B, kinetic energy is maximum, potential energy is 0. But that mass continue to go forward and start compressing the spring to the point that it goes to this other extreme. And what's happening at this other extreme? At this extreme end, the spring is compressed. So the potential energy is maximum. But think about the mass. mass goes on to this extreme position C, stops momentarily and reverses, which means the kinetic energy at point C is 0. So what is happening is we have these three locations where here potential energy is maximum, kinetic energy is 0. Here potential energy is maximum, kinetic energy is 0. And at point B, potential energy is 0 and kinetic energy is maximum. Do you agree with me? So you have this interaction of energy. This energy interaction keeps this system going. Energy can neither be created nor be destroyed. It can only change forms. That's why you have this continuous change of kinetic energy to potential energy to kinetic energy that makes that mass go forward and backward. Everyone understood this? Now imagine if you have some type of damping or some type of air resistance, then what's going to happen? In each oscillation, that air resistance is going to dampen or going to absorb some amount of energy from this energy interaction. So you start with kinetic energy of 10, then potential energy instead of becoming 10 becomes 9, 8, 7, 6, to the point when the total energy, which is the summation of kinetic and potential energy, equals to 0, and at that time mass stops. Everyone understood this? I use this energy word too many times because there is a reason for that. Energy methods are the methods, the most powerful methods that govern the dynamics of universe. So now what I'm going to do is I'm going to derive the equation of motion. I'm going to derive the equation of motion using Newton's law. That is super simple. Then I'm going to derive the equations of motion using Hamiltonian, which is an energy principle. And then I'm going to derive the equation of motion using Lagrangian, and that is also an energy method. Yeah.
So you're saying between kinetic energy and potential energy there that keeps going because of change until all the energy is dissipated.
Yeah, but if there is no energy dissipation, if energy is going to remain constant, these oscillations would continue for infinite period of time. That's why you have these planets and asteroids, they continuously move because there is no energy dissipation. Everyone understood this? So I know you probably have done this in your first statics and dynamics course, but what I want to do is I want to first show it to you how you derive the differential equation of motion, and then later I want to actually ask, I want to use Hamiltonian and Lagrangian to solve the problem. Now, before I derive the equation of motion, I want you, and this is pretty obvious, but I want you to understand, why do we need a differential equation of motion? Or why do we need to have, why there is a need for a mathematical expression? So as an engineer, I want to find out the future state of this mass as a given period function of time. So what I want to know is, initially at time t is equal to 0, the initial velocity is 0, and say there is an initial displacement. What I want to know is, where would the mass be when time t is equal to 5 seconds, 10 seconds, 15 seconds, 30 seconds? And that is the reason why I need some type of mathematical expression that would tell me that, hey, this is the mathematical expression. You solve that mathematical expression, and the solution will tell you where the mass is going to be, or the future state of mass. That is the same purpose for robot dynamics. What we are going to do is, we are going to derive an equation that describes the motion of the robot. And once we solve that equation, It could be a differential equation. Differential, if you want to solve, you use integration. It could be an algebraic equation, pluses and minuses. So you can solve some matrix methods and then try to find out the solution. So at the end of the day, as engineers, we want to understand how the system behaves. If the system behavior is something that we like, we are good. If the system behavior is something that we don't like, then we add a controller. That is going to be the discussion of the subsequent chapters. So first, for this simple problem, let me derive the equation of motion using Newton's law. And so what I'm going to do is think about it like we have this spring mass system. And what I'm going to do is I'm going to draw the free body diagram. So now consider this is position A. And at position A, the spring is completely stretched, which means the spring force acting on the mass. If my displacement, I'm going to give you some displacement and say my displacement is maybe X. So my displacement is X. So spring force is going to be Kx. And every action has equal and opposite reaction. So there is this spring force Kx over here. And now what I have is, since the mass is moving towards right-hand side, I'm going to use my velocity, displacement, and acceleration in this direction. So I'm gonna consider my velocity, displacement, and acceleration going towards right. Now I'm going to apply, this is my M. I'm gonna apply summation of forces is equal to mass times acceleration. Now please understand, and this is very important, never ever forget this. Coordinate systems are super important when you use Newton's law. That could be an advantage or that could be a disadvantage. Why it is an advantage? It is an advantage because if the problem is simple, you can just write the equation of motion, something like looking at the system dynamics. So in this particular problem, forces go on to the left. The force is spring force. Spring force is opposite to the positive x direction. So I'm going to say this is minus kx. Mass is a scalar quantity. Acceleration x double dot is in the same direction. Please note, acceleration is in the same direction as positive x direction. So this is going to be mx double dot. So which means my differential equation of motion is mx double dot plus kx is equal to 0. This is the differential equation of motion for this spring mass system. Do you agree with me? Now, the equation of motion is a differential equation. What is the order of this differential equation? The order of this differential equation is number of dots on x. So since there are 2 dots, this is a second order ordinary differential equation. Why is this called an ordinary differential equation? Because even though I did not state it, and in today's class, I'm going to go and clarify these fundamental basic concepts, because sometimes these concepts are not explained from engineering point of view. So why this is called an ordinary? Because x, which is the dependent variable, is the function of an independent variable t. And there is only one independent variable, one independent variable. If you have more than one independent variable, then it would become a partial differential equation. Since there is only one independent variable, this is an ordinary differential equation. This is the second order ordinary differential equations because it has 2 derivatives. Do you agree with me? What is the meaning of the solution of the differential equation? The meaning of the solution of the differential equation is find a function which is x of t. So some function that is given as x of t, when you take the first derivative, when you take the second derivative, and once you substitute those second derivative in this equation, the left hand side is equal to right hand side. That is the meaning of the solution of the differential equation. So we are trying to find out this function x as a function of time, wherein if I take the second derivative of this function, substitute in that expression, and if I substitute the value of x, the left hand side will be equal to right hand side. Everyone understood this? I don't know what you studied in differential equation class, but entire differential equation class can be taught in half an hour, and I will do that not today, in next class. So come prepared. So let's finish physics 321 in today's class. Next class we'll finish differential equations, because I don't believe in using different techniques to solve different problems. I believe in using one technique, but that technique is so robust that it will solve all the problems. And that is the only technique that I use. I have no interest in changing my tools to solve the problems at hand. Anyway, so what is the disadvantage of this approach, the Newton's law? The major disadvantage of Newton's law, I don't know if you noticed it, is drawing free body diagram. Which means if I have to use Newton's law, and if I give you a very complicated dynamical system, which is connected with multiple springs, multiple masses, multiple dampers, and if I ask you to come up with multiple degree of freedom differential equation, the first hurdle is you have to separate out those parts, assign the coordinate system, and then find out the free body diagrams. For simple problems, it's easy. But imagine if you have hundreds of these masses. Drawing free body diagram is not easy. And if you don't believe me, just imagine the truss problems that you solved in statics. Remember? And now imagine that truss starts moving. Then so the idea here is, now what we want to do is we want to use the energy-based method. So I will give you the first iteration of the energy-based method, and then I will give you the second iteration of the energy-based method. So what are the types of energies in this particular system? There is a kinetic energy and there is a potential energy. Do you agree with me? There is a kinetic energy, there is a potential energy. If you look at the dynamics, the total energy is going to remain constant, which means the kinetic energy will get converted to potential energy will get converted into kinetic energy, but sum of kinetic energy and potential energy is going to remain constant. Do you agree with me? Do you agree with me? That's what is causing this mass to vibrate. So what I'm going to do is, I'm going to write down the expression for kinetic energy. So kinetic energy is given by T. Kinetic energy.
Constant in case where there is no dissipation.
Yes, right now there is no dissipation. So kinetic energy is given as 1/2 mv square. So 1/2 mx dot square. Do you agree with me? Potential energy is given as V, and that is, if you think about it, it is the area under this curve or area under this line, which is given as, this is kx, this is x, and it's a triangle, so there's going to be 1/2 k times x square. This is the potential energy. So the total energy, and this is super important concept, because there is a whole body of knowledge which is called as Lyapuna methods. They are all based on this concept. So if you take some electrical engineering courses, control courses, the concept of Lyapuna, then it's all based on this. Total energy is equal to T plus V. Are you with me? There is a special word for this. It is called as Hamiltonian. So now total energy is T plus V, is 1/2 m x dot square plus 1/2 k x square. Now I'm going to ask you this simple question, and this comes from the physical understanding of problem. If my total energy is constant, if I take the time derivative of the total energy, what would it be? Zero. Everyone agrees with me? If my total energy is constant, if I were to take the time derivative, which means rate of change of energy with respect to time, it will be zero because the energy is constant. Everyone agrees? This comes from the physics of the problem. I didn't invent this. So this is what I'm saying. So what I'm going to do is, I'm going to take the derivative of total energy, which is d by dt of total energy. And d by dt of total energy is, please understand, it's going to be 1/2. M is constant, M stays as is. Derivative of x dot square. Remember, we have to use the chain rule because x is function of time. X dot is function of x. So basically this will become 2x dot and d by dx by dt plus 1/2 k 2x, and let's not forget x is a function of time, so dx by dt. Do you agree with me? Since the total energy is zero, I'm going to put a big zero and then I'm going to cancel out the common terms. So basically I get 2x, so this becomes, so 2x dot, and then this is going to be m x double dot plus k x is equal to 0. So as you can see that once I solve this, I get this equation, which is mx double dot plus kx is equal to 0. And this expression is the exact same expression that we derived. The only issue here is that we did not have to calculate the free body diagram, or we did not derive the expressions, or we did not assign the coordinate system, but still I got the same expression. So this is, yeah.
On the
Yeah. No, what did I make a mistake? So x dot square. No, kx, because x got cancelled and I took it. So there is x dot here, there is x dot here. So I cancelled those out. Okay, I probably did not write this properly. So 1/2 m x dot becomes 2 x dot x double dot plus 1/2 k 2x x dot. So now this is equal to 0. So can you see that this x dot, this x dot gets cancelled, this gets cancelled, this gets cancelled, and now you have mx double dot plus kx is equal to 0. Does that make sense? Yeah. Now what I want to do is, this is Hamiltonian, but Hamiltonian technique, actually let me so this, what I have shown over here is the essence of a class of techniques known as Lyapuna techniques. So the idea is, if you have a system what you do is you define an energy function for the system and see if that energy function is staying same, increasing or decreasing. If that energy function is staying constant, then that system is said to be in stable equilibrium. If that energy function is increasing as the time goes on, then the system is unstable. And if that energy function decreases over time, then the system is asymptotically stable. So these are class of problems which are called Lyapuna based problems. And there is a whole body of literature on Lyapuna based techniques, uh, Lyapuna redesign controls. If you take Professor Zhang's class or some linear systems class at Tempe, they will spend a lot of time on talking about Lyapuna based techniques. But why Lyapuna based techniques are powerful? Because remember this, Lyapuna based techniques are dependent on the laws of nature. These are called conservation laws. These are universal laws that govern you, me, and universe. Okay, so and these laws are valid at even at quantum level, and these laws are valid at a planetary level. So now what I want to do is, but Lyapuna based techniques is good, but there is one more powerful technique, and that is the technique of my choice. Because please try to understand, I have no interest in taking derivatives and writing the derivatives by hand. Okay, so the technique which I'm going to tell you can be easily programmed inside MATLAB, and MATLAB, once you substitute the values of potential energy, values of kinetic energy, MATLAB would do its calculation and give you the motions, equations of motion. This technique is called as Lagrangian technique. How many of you are familiar with Lagrangian dynamics? Okay, so if you are not, please understand this is a very powerful technique. Lagrangian dynamics. Idea is the same. Now, instead of defining the Hamiltonian, Hamiltonian is the sum of potential energy and kinetic energy. I'm going to define the Lagrangian, which is the difference between the kinetic energy and potential energy. So Lagrangian is the difference between kinetic energy and potential energy. Okay. And the idea is first form the Lagrangian. And then what you do is the equations of motion are given as using the Lagrangian equation of motion. 0 is equal to d by dt partial L by partial x dot minus partial L by partial x. Now, why is this partial coming in the picture? Because please try to understand, kinetic energy has a velocity term. Potential energy has a displacement term. Do you agree with me? This Lagrangian, what I have defined, is defined as the function of kinetic energy and potential energy. In other words, velocity and displacement. So now this Lagrangian is dependent on x and x dot. So I'm interested in finding out the derivative of Lagrangian with respect to velocity and the derivative of Lagrangian with respect to displacement. Do you agree with me? So now what I'm going to do is I'm going to form this Lagrangian. Now kinetic energy 1/2 m x dot square minus potential energy 1/2 k x square. And then for this very first problem, I'm gonna separate out the terms, because the killer in the Lagrangian technique is making sure of that negative sign. I promise you that If you are not familiar or if you are not careful, your signs will get wrong. So make sure. That's why I don't like solving by hand. So that's why we have a computer program that would implement this in MATLAB. So what I'm going to do is I'm going to take partial L by partial x dot. Partial L by partial x dot, which means all derivatives, all x values are considered to be 0. So which means I would be considering 1/2 m to x dot. Since x is treated as 0, so plus this is going to be 0. Then I'm going to do partial L by partial x. And then please understand, the first term is x dot. So whatever derivatives I get, which is x dot, is going to be 0. So that means the first term is 0 and second term is minus 1/2 k times 2x. So this term is going to become m x dot. Are you with me? And the second term is going to become minus kx. Are you with me so far? Everyone understood how I took partial derivatives? I'm looking at my undergraduate students. No, yes, this is the time to ask. And then what I'm going to do is I'm going to substitute partial L by partial x. This quantity here and this quantity here. So this equation is now going to become d by dt. Please understand, this is the full derivative. Partial L by partial x dot is m x dot minus partial L by partial x is minus kx. And now, since this is the full derivative, this equation becomes mx double dot plus kx is equal to 0. Are you with me so far? Yeah. Any questions here? So I'm going to work out few more problems, but this is what we are going to do. No matter how complex our robot is going to look like, we are going to solve forward kinematics. Everyone comfortable with forward kinematics? Then after forward kinematics, do you agree with me? I'm going to get Px, Py, Pz's. Those are the end effector positions. Px, Py, Pz. I will use MATLAB to find the derivatives Vx, Vy, and Vz. Do you agree with me? Once I know Px, Py, Pz, Vx, Vy, Vz, do you agree with me? I can find out the kinetic energy as 1/2 m multiplied by Vx square plus 1/2 m multiplied by Vy square plus 1/2 m multiplied by Vz square. Do you agree with me? Next part is finding out the potential energy. Potential energy, if there is a spring, the potential energy is given as it gives me potential energy, information about potential energy. Okay, so potential energy is, if it's a spring, it's K multiplied by displacement square. Remember, displacement is nothing but Px, Py, Pz. So displacement square. If it's some mass located at some distance, remember m times g times h. So once I got the potential energy, once I got the kinetic energy, I would form the Lagrangian L. I would form Lagrangian and run MATLAB code. Run MATLAB code that will perform this jugglery. And at the end, it will just MATLAB will give me this expression. And once I have this expression, I can use ODE 45. Have you done the online course on solving differential equations using MATLAB? No, that was part of the first. So then once you have the differential equation, then you use ODE 45 and solve it. Yeah.
When you say potential energy, are we scanning for springs or doing like gravitational?
So depending upon how the robot is constructed, you can consider the potential energy. Because let me take one more example where I take the gravitational potential energy. Just bear with me for a second. So this all we are gonna do. By now, you should be champions of forward kinematics, right? Now, given a robot arm, we will use the homogeneous transformation forward. You do forward kinematics, and then finally get the expression for Px, Py, Pz. And then what we do is we find kinetic energy by differentiating Px, Py, and Pz. Then we find the potential energy either based on the springs or based on where the masses are located and form Lagrangian. And once you got that, MATLAB will take over and do this. I'll share you the code that actually does this. And then MATLAB will give you this expression. And then you can use ODE45 or ODE23 or some other tool to solve that expression. And if you want, you can connect, actually, you can send that output of that solution to a sim mechanics model, and it will actually simulate your robot arm. So that is what the robot dynamics is all about. And Lagrangian technique is so robust, whether your robot arm is 6 degrees of freedom, 10 degrees of freedom, 100 degrees of freedom, it will give workout. So Newton's laws are great, but energy methods, Lagrangian methods are my methods of choice, because guess why? I'm just dealing with scalar quantities. Energy is a scalar quantity. Do you agree with me? Potential energy is a scalar quantity. So what I have is Lagrangian, the scalar, which means I don't need to worry about coordinate system. I don't need to worry about the direction of forces. And then, boom, I got the differential equations of motion. So that is all we are going to do in next 3 or 4 classes. Okay. Now what I want to do is I want to take one more example wherein instead of translating mass, we have a pendulum. So let me work out the same problem. So consider that we have a pendulum. And this pendulum has length L. This angle is theta. Let me specify the coordinate system. And I'm specifying the coordinate system because I will solve this problem using Newton's law, Hamiltonian method, and Lagrangian method. So X, Y, Z is coming out. Now, please understand that it's very important that I show the direction of theta. So Newton's law is in the translation, summation of forces is equal to mass times acceleration. And when you are in the rotational coordinates, you have summation of torque is equal to I times alpha. And remember the important thing that I talked about in last class, that this expression is not a blanket expression that you can apply anywhere you want. This expression, let me explain it to you what this expression physically means. Please understand, you have torque on one side. Torque is twisting moment. Moment cannot be about arbitrary point. Moment has to be about specific point. So for example, all this expression, this torque is a moment. That moment is about a certain point. And it is not evident in this equation where that point is. But that point could be either a fixed point or could be the center of gravity or the point which has the velocity v cross r is equal to 0. And we'll take those cases step by step. But what that means is this expression, what this expression is telling me, that this expression is valid if this is my point O, this expression is valid about point O. Now, why this point O is important? Because please understand, I stands for mass moment of inertia. I stand for mass moment of inertia. What is the mass moment of inertia? Mass moment of inertia is given as mass multiplied by the radius of gyration square. So for an example, what is the meaning of gyrating? Gyrating means moving. So basically, I naught is nothing but mass moment of inertia. And this mass moment of inertia, please understand, it has the word moment. So it is dependent on where you take that mass moment of inertia. So for an example, for this simple pendulum, since that pendulum is pivoted at point O, this is mass M, this is length L, mass moment of inertia is mass multiplied by the radius of gyration square. Gyration means moving. So this is M times L square. Now, if you express this expression, and it can be derived. If you take this expression about the center of mass, you will get the exact same answer. If you take this about the center of the mass, you will get the exact same answer. But at that time, your radius of gyration is going to be different. Radius of gyration would be 0. Everyone understood this? Still, you will get the same expression, and I will derive that in next class. So you have something like this. So what I'm going to do is, I'm going to use the Newton's law first. As per the Newton's law, you have gravity, it is going down. This is M. So you have the force M times G. This distance is L sine theta. So what I want to do is, I want to write down the forces, basically torques on this mass. So as I can see, I have summation of torques is equal to I times alpha. What are the torques? Torque is M times G multiplied by L sine theta. Force multiplied by lever arm. Now, whether is this torque positive or negative? Curl your fingers in the direction of the torque. Curl your fingers in the direction of the torque. Your thumb is opposite to positive z direction. Do you agree with me? Which means this torque is negative. So if you look at this, this torque is like this. So curl your fingers and you will see that this torque is negative. But now look at theta. Theta is, curl your fingers in the direction of theta. Theta, theta dot, theta double dot are in the same direction. So which means theta, theta dot, theta double dot are positive. You agree with me? Curl your fingers. So what I have here is I multiplied by theta double dot. So if I write this equation down, this becomes I theta double dot plus M GL sine theta is equal to 0. Now I, as we know, is M times L square, M times L square theta double dot plus M GL sine theta is equal to 0. I can divide both sides by L square and M. So I get the expression theta double dot plus G over L sine theta is equal to 0. Do you agree with me? Now, my question to you is, what is the order of the differential equation? 2. Why the order is 2? Because check 2 dots. 2 dots. So second order. Is this an ordinary differential equation or a partial differential equation? This is ordinary. Why it's an ordinary differential equation? Because theta is only function of time. Theta is not function of anything else. Theta is only function of time. Now here comes the important question. Is this equation linear or non-linear? Mx double dot plus kx is equal to 0. This again is a differential equation, ordinary differential equation. But is it linear or non-linear? That equation mx double dot plus kx, this is a linear expression. And since, please understand, sine theta is not a straight line. Sine theta is not a straight line, but instead sine theta is something like this. That's why this function, since sine theta is non-linear, this function or this equation is non-linear. Do you agree with me? Yeah.
The solution of that function would be in terms of E, right? How would that be linear?
No. We will talk about solution. We are not to the solution yet. Right now, we are just formulating. I will talk about the solution and we will dissect what it means by solution, what are the techniques and all that. But right now, what I want to tell you is we have these two differential equations. One equation is linear, other equation is non-linear. Now, please understand, what do I mean by, okay, what is linear and non-linear? One burger for $1, 2 burgers for $2. This is all linear, right? But 5 burgers for $3 is non-linear. Okay, go to McDonald's, 1 burger $1, 2 burger $2. But then what you do is you give them $3 and they have a deal, and instead of giving 3 burgers, they give you 5 burgers. The system became non-linear. So what that means is, if I were to put a straight line approximation here, then here I can approximate sine theta as theta, and in this small region, and this region is about 17 degrees, if the oscillations are within 17 degrees, this expression can be expressed or can be approximated as theta double dot plus g over L, theta is equal to 0. So this expression, when theta is less than equal to 17 degrees. And you can check this out. So you can see sine 17 is equal to 17 divided by 180 multiplied by pi radians. And you will see that these two numbers are same. Now that's why you have seen these old grandfather clocks. Basically, the pendulum is sort of going in a very small oscillation. There are physical stops that prevent that pendulum from going out of 17 degrees limit. Now let's try to derive the same expression using the energy technique. So first, I'm going to write down the expression for kinetic energy. Kinetic energy for rotational object is 1/2 I theta dot square, which is mass moment of inertia multiplied by the angular velocity square. And the potential energy is, now potential energy is depending upon potential. So where your datum is. So for an example, if my datum is over here, this is my H. So this is going to be minus M times G, and H is L cosine theta. Do you agree with me? Because I'm going below datum. If I go above datum, then it will be positive. But my datum is where my O is or 0 is, and I'm going down. See, mass is below the datum, That's why I have m times g multiplied by the vertical distance, which is L cosine theta. Do you agree with me? Now what I'm going to do is, I'm going to first solve this using Hamiltonian technique. H, which is T plus V, which is 1/2 I theta dot square minus mgl cosine of theta. And now I'm going to take the derivative d by dt, and I'm going to substitute is equal to 0. So this expression becomes 1/2 I multiplied by 2 times theta dot, theta double dot, minus m is a constant, g is a constant, L is a constant, cosine theta taken the derivative becomes minus sine theta. Again, by chain rule, I need to multiply this by theta dot is equal to 0. So now with this, half gets cancelled, half gets cancelled, this gets cancelled with this, and I have the expression I theta double dot plus mgl sine theta is equal to 0. And I can make the substitution I is equal to ml square, and then I would get the same expression which is shown over here. Everyone agrees with this? The last part is I want to solve this equation, and I'm going to do this only once. From next, yeah.
Can you please describe how potential energy is negative?
Okay. So potential energy depends upon the potential. So if this is my datum, if my mass is below the datum, it has negative potential energy. If my mass is above the datum, I have positive potential energy. Datum you can take anywhere. What it means is the exact same expression. You will get the exact same expression if instead of taking datum here, if you take datum here. So if you take datum here, this is your datum. Then your H is going to be this. But in that case, mgh, this is your m times g times h, m, g, and your h is going to be L minus L cosine theta. And you can actually substitute the positive potential energy in that expression. So here you have negative. So here your V will be positive. And then do the exact same jugglery and you will get the same expression. So potential energy is dependent on your datum. If your datum is above the mass, potential energy is negative. If your datum is below mass, potential energy is positive. Yeah.
So when you have like the V equals negative mg L cosine theta, what's the dot cosine theta?
There is no dot. Oh, cosine, which cosine theta?
Um,
Oh, this dot?
here the H, yeah.
No dot.
Then isn't it T minus V?
No, wait. The T minus V is coming. It's not there yet. This is Hamiltonian. So what I did, I differentiated the Hamiltonian and equated to 0. Do you agree with me? I did not use the Lagrangian techniques yet. Now I want to solve this using Lagrangian. And I'm not going to do this from next class. What I would do is I would just jump on to the Lagrangian techniques, and then we will use MATLAB to derive the equation, solve the equation. But I want to do this for these problems so that you understand that these are 3 different techniques. They will give you the exact same answer. Lagrangian L is equal to T minus V. T is 1/2 I theta dot square minus V is, can you see potential energy is minus M times G times L cosine of theta. And the Lagrangian dynamics equation is d by dt partial L by the velocity. Our velocity is theta dot minus partial L by partial theta. And now I'm going to use this expression directly. It's going to be 1/2 I theta dot square plus mgl cosine theta. So first I need to find out this guy. D by dt is going to be 1/2 I 2 theta dot. Why there is no d by theta double dot? Because this is with respect to theta dot. Okay, this is not with respect to t, this is with respect to theta dot. Minus, I'm going to get 0 here. Cosine becomes minus sign. Is equal to 0. Now here, this 1/2 cancels with this 1/2. Now I need to take the derivative of that quantity in between. I is a constant, so it comes out of the expression. Theta dot becomes theta double dot plus mgl sine theta is equal to 0. So in today's class, finally, we got the same expression. So I taught you 3 techniques to derive the differential equations of motion. And I did not talk about the conservative and non-conservative forces, but we'll talk about those. That is where the method of virtual work will come in the picture. But yeah, question?
Yes, Professor. So here in this term, you have take a partial differential for both the terms, right? For
Correct.
theta dot square and mg sine.
Yeah.
Okay, and this constant for 0. Okay.
Yeah.
got
So
it.
this guy implies theta is equal to 0. This guy implies theta dot is equal to 0. So basically that is what it's with respect to. So if so, I'm sorry, I shouldn't call this 0. I should say constant. So theta dot is equal to constant, and theta is equal to constant. So with this, and in the next class, what I'm going to do is, I'm not going to write these equations by hand. I would actually, as a matter of fact, code is already uploaded on Canvas. You can look at the MATLAB code. Once you substitute the Lagrangian, somehow you find the kinetic energy, potential energy, and substitute the equation for Lagrangian, MATLAB will implement this equation symbolically and give you the answer. Yeah.
So your kinetic energy is equal to your change in your L over your change in theta dot.
You mean L?
Yeah.
L is the Lagrangian. Lagrangian is the difference between
It's a
the kinetic energy T minus the potential energy V.
the second part is EL over D theta.
DL over D theta is the Lagrangian, is this big expression. I have taken the partial derivative theta dot minus partial derivative of L. Yeah. Here there is no theta double dot. The partial derivative.